We tried. All right, alkanes. Alkanes. That is the simplest class of organic compound. Now, you all have dealt with alkanes in the past. Things like gasoline are alkanes. We've all dealt with. They're ubiquitous in our life. We use them all the time. Now, here's a few quick points about alkanes and organic compounds in general. Organic compounds are almost, well, I will say this, they're always made of carbon. They're always made of carbon. They have to have at least one. Most of them have more than that, but they have to have at least one. They have a ton of hydrogen, usually. Not always, but typically they have a ton of hydrogen. Every now and then they'll throw in some oxygen, sulfurs, nitrogen, halogen, and any other element on the periodic table, including metals you can get with organic compounds. It's kind of weird, but you can get it. And you always write the carbon atom first. Whenever you're writing an organic molecules formula, you write the carbon first, the hydrogen second, and then all the atoms after that come in alphabetical order. Okay? So for example, a formula for it could be CH4O. That would be an example of an organic compound. That's not an alkane, but it's an example of an organic compound. CH4O, CH3ClO. There's another example. The chlorine comes before the oxygen simply because in the alphabet, C comes before O. Carbon and hydrogen are first. That's very simple. Okay, so that's just a quick and brief description of organic compounds, but they're very simple. They're made of carbon. So we, you and me, are organic. We're made of tons of carbon. There's lots of carbon in our body, including hydrogens, tons of that, oxygen, sulfurs, all that other good stuff that makes up people. All right, here are some typical properties. All organic compounds are made of covalent bonds. We'll think about that in a second. They have typically low melting points. Not always, but typically. They have low boiling points. Not always, but typically. They are very flammable. Usually. I think all organic compounds that I know of are flammable. There's probably a few exceptions to that rule, but gasoline, for example, you can burn it up pretty good. Sugar, that's organic. I'm sure everyone here has burnt sugar before. It smells pretty good, tastes even better. Soluble in non-polar solvents, so things like gasoline don't dissolve in water, so they're not polar, non-polar. Organic compounds are typically non-polar. Now there's plenty of examples of ones that are polar, but typically organic compounds are not polar and not soluble in water. Now the alkanes for sure, which we're going to get into here in a second, the alkanes are generally, I think all of them are not soluble in water, just insoluble. Now here we have an illustration where we have a beaker or a flask or whatever. They're pouring some oil into it. Everyone in this room knows that oil will not dissolve in water. If you don't believe me, go to Publix, pick up a bottle of Wishbone Italian salad dressing. The brand I use. If you shake it, it'll have like an emulsion going through it. But if you let it sit, you'll have a layer on top and a layer on the bottom. You've all seen that, yeah? That's because the top layer is oil, probably olive oil. Bottom layer is water, so that they don't mix. Make sense? So organic compounds in general don't mix well with water in general. Some of them do. Now let's compare an organic compound to an inorganic compound. Inorganic simply means not organic. So if you're not organic, you don't contain carbon. That's pretty logical, right? So sodium chloride, table salt. That's a great example of an inorganic compound. Has a sodium plus and a Cl minus. Now, don't do this, but if you were crazy like me, you would try this. But don't, please don't do this. You'll ruin your house. Ask my mother. Now, if you take sodium chloride and try to burn it with a lighter, say a barbecue lighter, you'll have a really hard time doing that. It won't burn. Now the reason I say don't do it is a lot of times sodium chloride has some water stuck in it, and if you heat it up too much, the water will escape, and the salt will do what's called popcorning, and it'll fly everywhere. And it's really hot when it's flying, and it really burns you badly. Ow. when you do it. Yeah, I was young once. Now, try to burn sugar. Now, you probably won't want to do this because it'll stink up your house for a while. But if you've ever made flambé, what's the other one, the French one? Creme brulee. They burn the sugar. So you can easily burn sugar. You just leave a torch and it burns up pretty good. Sugar is organic. Salt is inorganic. Sugar will burn quite easily. Salt takes a lot of energy to burn. Okay, so salts are considered not flammable. Organic compounds are flammable. You can dissolve sodium chloride in water all day long. You can't dissolve motor oil in water, for example. So salts, inorganic compounds, are generally thought to be soluble in water. Organic compounds are generally thought to be insoluble in water. Now again, there's exceptions to all that. There are lots of organic compounds that will dissolve in water, sugar being one of them. And there are some inorganic molecules that won't dissolve in water at all. So there are exceptions to both of those rules, but in general, that's how it works. All right? So now, real quick, this should be a learning check here. Identify the characteristics as most typical of compounds that are inorganic or organic. They have a high melting point. Inorganic, table salt, for example, won't melt very easily. Okay? You can melt typical organic compounds because they're usually liquids at room temperature. B, not soluble in water. Organic things are not soluble in water typically. Has a formula. Oh, there it is. CH3. Stop right there. It's got carbon, right? So it's got to be organic. Has a formula. MgCl2. There's any carbon there? No, so it must be inorganic. Very good. What else we got? Burns easily in air. Think about the flambé, guys. Think about the creme brulee. Burns easily in air. Tastes good too. Has covalent bonds. Organic. Let's think about that for a minute.
Chicken is very good with burning sugar.
Keep talking. I love chicken. Keep talking. Hey, why'd you stop? You get me all set up for chicken talk and then you stop? Come on. I like me some chicken wings from Publix. But I'm allergic to them.
What? Wow.
They swell up. My pants shrink in the dryer. You know what I mean? So, haven't had chicken wings in 6 months. Hi, I'm Dr. Betts. I'm a recovering chicken addict. God, I love those things. They're so good, right? Anyway, you got me on chicken now, sorry. Covalent bonds. Let's talk about that. Covalent bonds. Now, think about your body for a second. Everyone in this room has probably taken a lot of biology courses. You guys know that we're, what, 70% H2O? Something like that? A lot of water inside the human body, right? And we also just learned that things like salts, inorganic compounds, are soluble in water. And that's an ionic bond, right? Now we know that organic molecules are covalent. And we should know, because we talked about it earlier, that covalent bonds, for example, if you and I had a covalent bond, we'd be physically connected, right? So if I go this way, she's coming with me. If she goes that way, I got to follow her because we have a physical connection, right? If we were ionic, she'd be negative or positive, I'd be negative. Dissolved in water, I'd go my way, she'd go hers. We're not connected. Now think about that. You're 70% H2O. If you didn't have this connection, whoops, and we dissolved in water, what would we look like? We'd be liquefied because we wouldn't have any structural integrity to hold us together. Pull on your skin. Isn't that neat? Your skin doesn't fall apart, does it? Because it's covalently bonded together. You are the product of millions and millions of small little bonds. Isn't that freaky? I'm going with you to bed tonight. What happens if those bonds decide they don't want to be together anymore? Right? But you are, literally, I make light of it, but we are. We're just a bunch of covalent bonds holding our molecules together. And we're going to learn in the subsequent chapters other types of interactions that our molecules will make us even stronger. So we can pull on our skin and our tendons don't rip and stuff like that. But it all reflects and all revolves around covalent bonds. Isn't that neat? We are a product of covalence. Isn't that cool? And everyone says, yes, Dr. Betts, that's very fascinating. Thank you for bringing that up. No one said it, I guess. All right. So we've done this before, so I'm going to run through it just real quick because we've already seen this kind of stuff. When you have organic molecule. They're covalently bonded together. So if we have, say, the formula CH4, we look at the periodic table and we find carbon. You say, okay, carbon has how many valence electrons? 4. And hydrogen has how many valence electrons? 1. Right?
Yep.
So carbon wants to make how many bonds? 4. Carbon needs to make 4 bonds in order to have an octet. Remember all that? We're going back in the archives now a little bit, right? Everybody?
Yes.
More than 3 people?
Yes.
All right, we got 6 people now. Good. So now, carbon wants to make 4 bonds. So it's no coincidence that there's 4 hydrogens there. Right? That makes logical sense, doesn't it? Carbon wants to make 4 bonds, there are 4 hydrogens. That works out pretty darn well. So what happens is, the carbon will bond to hydrogen 4 times. Something like that. And we've already learned that that's going to have a tetrahedral shape, which is like a little pyramid kind of thing. And we've all learned about that. So now, let's think for a minute about that. We have carbon wants to make at least 4 bonds. If it's bonded like that, it's going to be like tetrahedral, 3-dimensional. You know, the molecule has 3 dimensions, height, width, and length. And we all have height, width, and length too, don't we? Not a coincidence. We are the product of covalent bonds, which I think is absolutely fascinating. Now, if you have a alkane with CH4, with that formula, that is actually called methane. It's affectionately known as methane, CH4. Okay, you have to know that. That's CH4, that's methane. Now, what if we had, C2H6. Okay, we've just made the formula a little more complicated. Now there's 2 carbons. Wow, 2 carbons. What's the structure of that look like? Well, let's put it together here. A couple of carbons, we'll bond those bad boys together, just like that. And then we'll put a bunch of hydrogens around it. So 1, 2, 3, 1, 2, 3. Now let me cover this carbon up right quick. How many bonds does that carbon have?
3.
How many bonds does that carbon have total?
4.
4. So the octet rule is satisfied for that carbon, right?
Yes.
It only has 3 hydrogens, but it's also bonded to this carbon over here, right? Same for this carbon, yes?
Yes.
So both carbons have an octet. Does everyone agree?
Yes.
All right. This one is called ethane. Draw that a little bigger, sorry. That one's affectionately known as ethane. That's its name. So whenever you see C2H6, or you see this structure right here, that is ethane. If you say that word to any chemist in the world, they will draw this. Okay, if they can't, find a different chemist. All right, every chemist can do that. That's ethane. Now the next one, C3H68. That's like this. 3 carbons in a linear chain. H, 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 H. Oh my goodness, so many H's. Whew. Does every carbon in that structure have an octet?
Yes.
Yes, they do. That one is called propane. Hey, we know propane, right? Anybody who likes to grill likes the propane. If you're a purist, you use charcoal. Just saying. Propane. C3H8. If you say propane to any chemist in the world, they will draw that molecule right there. Doesn't matter what language they speak either. They speak English, they speak German, they speak Italian, Japanese, Chinese, does not matter. They will draw that molecule from that word, because that's its name. Next in the series of alkanes, C4H10. Carbons, 4 of them, in a chain. lot of carbons now. We got 4 of them bad boys in the chain. Does every carbon in that structure have 4 bonds?
Yes.
Yes. So that's an acceptable carbon structure. This one is called butane. Butane. Everybody calls it that. Everyone recognizes butane. That's the structure of butane. Now, these 4 right here, you have to know 1 through 10. You have to know 1 through 10. These 4 are by far the most difficult because their names don't have any basis in mathematics. Propane, butane, ethane, methane, they don't really mean anything in terms of math. These names have been around for quite a while. So you kind of have to memorize these. So you have to know the CH4 is methane, C2H6 is ethane, that's the structure, that's propane. You kind of have to memorize them. Now the next series I'm going to show you, the 5 through 10, well, I will probably only go to 9, maybe 8, because they get really hard to draw. They follow math. Now if I were to ask you guys, what is a 5-sided shape in math called? A pentagon, right? So pent means 5, right? A hexagon is a 6-sided shape. Hex means 6, right? So if I were to say pentane, P-E-N-T, pent, how many carbons do I have? I have 5. See how it follows math? Yeah. So octane is like an octagon, has 8. Heptane.
7.
Aye, all right. Round of applause for the math people over here. Most people get that one wrong because that's a weird one. Heptane? Heptagon. I've never even seen a heptagon of you. Maybe you guys have. Okay. What about nonane?
9.
Ah, okay. You guys got it made in the shape. It's easy, right? It follows math. So if I have nonane, I have how many carbons? 9. It's that easy, right? That's all there is to it. These ones don't follow math. Propane. What's the 3-sided geometric shape?
Triangle.
Triangle. It's not triane, it's propane. You just have to memorize it. Okay? So those 4 are by far the most difficult because you have to memorize them. Now, let's get into the next ones. Let's just draw them real quick. Whew. C5H12. Carbon, 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 hydrogen, 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 another hydrogen up there, another one over here, one down there, one over here, one up there, one over here, one down there, and one up there. Okay, holy smokes, that's getting a little difficult to draw. Oh my goodness. That one's called pentane. Pent. P-E-N-T. 5-sided geometric shape is a pentagon. That's called pentane. Yeah.
Are you gonna, for the test, you're gonna give us the C5H12
Yep.
and we have to
Well, maybe.
draw
I'll probably
it?
give you the structure.
Oh, and then we have to know
Yep.
it's C5H12? Or
Well, if
the
I
name,
give you this, if I gave you the structure, you could actually just count the formula.
or we have to know the actual name?
Yep, absolutely. But the pentane's easy, right? It's 5 carbons. The other ones are a little more harder because you have to memorize. All right, let's go to the next one. C6H14. And everyone's like, man, this is getting hard to draw. And you're right. Okay, here we go. C6H14. Carbon to carbon to carbon to carbon to carbon to carbon. 1, 2, 3, 4, 5, 6. Hydrogen, 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 hydrogen. Another hydrogen up there, another hydrogen down there, another hydrogen over here, one there, a couple more over here, and we have 3 more over here, and my arm is ready to fall off, and I'm sure yours is too. That is hexane. Now, you guys are probably wondering if I'm really going to go all the way to 10 doing this. And I'm wondering the same thing. Now, we're smart people, everyone in this room. We can probably think of a better way to do this, right? Except for drawing up all these bonds and all this kind of stuff. There's probably an easier, simpler, and more obvious way. Because, I mean, I think if you look at the structure, your eyes kind of look at it and they kind of just glaze a little bit because it's really hard to see the forest through the trees. There's just a lot going on here, right? So let's think of an easier way. Well, let's just take another color here. Let's just take blue. Let's just draw a line, just a dotted line down through these bonds. Just draw a dotted line down through the carbon-carbon bonds, just like that, just straight on down. Okay, so now, I just want to consider what's between the lines. So here, on this side of the line, I have a carbon and 3 hydrogens. Is that true? On this side of the blue line, there's a carbon and 3 hydrogens. We all agree? So why don't we just abbreviate that? Why don't we just call it CH3? Line. Does that make sense? Is that easier? It's a lot easier, isn't it? So between these two lines, what's that? CH? Everybody? CH2, right. What's that one? CH2 again, so draw a line, CH2. These lines mean that these two carbons are bonded together. Line, CH2, line, CH2, line, CH3. Let's get rid of some of this excess dotting here. So, what does this mean? Well, this means that this carbon here is bonded to that carbon there. This carbon right here has 3 hydrogens attached to it as well. That carbon has 2 hydrogens. This carbon has 2 hydrogens. This one has 2 hydrogens. That one has 2 hydrogens. And that one has 3 hydrogens. That's easier. That's more obvious too, isn't it? It's nicer. It's a nicer way to look at it. But people are lazy. I'm lazy. I don't want to draw that either. There's an easier way beyond that. And you're thinking, get out of town. There's no easier way than that. In fact, there's a much easier way. But it takes a little bit of imagination on our part. Now, before I get into that, let's talk a little bit about shape. Now, we talked about this, and I want to bring it up again. These carbons are not flat. They're tetrahedral. They have 3-dimensional shape. And please don't think about these things as being static, not moving things. They are very flexible, very movable, and they're always trying to move. Now, why would they want to move? That takes energy to move, right? Why would they want to do that? Oh, you have to think about this. What do those little lines mean? What's inside this line here? Like, what does that line represent? It's a bond. What makes a bond? Electrons, right? So every one of these lines represents 2 electrons, right? So there's 2 electrons stuck there. Electrons are negative, right? Electrons hate other electrons. They're like, you know, cat and mice, I guess. They're like, ugh, hate each other. So they want to repel one another, right? They want to push against each other. Does that make sense? So these electrons here are pushing against all these ones around it. They're like, get out of here. I don't want you around me. So wouldn't it make sense then that they would try to find space where there were no electrons? Or less of them anyway? That would make sense, right? So what I'm about to show you is what the shape of the molecule will look like when it's at its lowest energy form. When all the hydrogens and carbons and all the electrons have the most space. Okay? Now believe it or not, they adopt what's called a zigzag. A zigzag formula. So here's a CH3 here. CH2 goes up. CH2 goes down. That's why it's called a zigzag, because this repeats. Okay? So that's called a zigzag formula. So it starts here, up, down, up, down, up, down. When you do that, I think you guys can agree that this carbon is pretty far away from that one. These hydrogens are pretty far away from those ones. So it gives itself a lot of space when it does that. Molecules always want more space. And so do chemists, by the way. So giving your molecule more space gives it lower energy. Okay? Kind of like you, right? Nobody wants anyone else in their business, right? It's better to have people further away from you. Just because you're more comfortable that way.
Families.
What's that?
Family members.
That's why electrons hate each other. They're all in the same family. But they love each other, but they hate each other. Now, they're going to try to get more room. And they adopt the zigzag shape to do that. But now there's a really obvious pattern here, right? Up, down, up, down, up. If there was another carbon, it would be down. If there was another carbon, it would be up. There's an obvious pattern developing here, right? We can exploit that pattern. Watch this. Let's get rid of that one. That is that. You can shake your head. It doesn't make any sense right now, does it? This represents that. How in the heck can that be? Watch this now. Watch this. You have a line that terminates right there. Okay? That line terminates at that spot. Can everyone agree with me? The line stops right there.
Yes.
And it goes to here. What I'm telling you is that wherever a line stops and wherever it comes to another line, so here and here, those are carbons right there. That's a carbon and that's a carbon. Okay? Down here, see how it goes and then turns? That's a carbon. Follow me? Everybody?
Yes.
Over here? What about this? What's that?
Carbon.
Everyone say it.
Carbon.
What's that? Louder.
Carbon.
Louder.
Carbon.
There we go. What's that?
Carbon.
They're all carbons, right? Everywhere a line terminates and everywhere 2 or 3 lines come together, there's a carbon. Make some sense? At least a little bit? Okay? Now, if that is carbon, let's just draw it there. If that is carbon, you don't draw, in a line drawing, you never draw the carbons in. Well, let's just draw it there for illustration purposes. If this is a carbon, and we know carbon has to have how many bonds? 4. Everyone say 4.
4.
Carbon has to have how many bonds?
4.
Louder. How many?
4.
4. It has to have 4. This carbon has 1 line from it, right? So how many bonds does it have at this moment? 1. What must the other bonds be? Say louder.
Hydrogen.
Louder again.
Hydrogen.
Hydrogen. It only has 1 line, so it has to have 3 hydrogen. We don't draw them in normally in a line drawing, but we know they're there. It's like in math. You have a number, you know that number is divided by 1, but you never draw it there, do you? But you know it's there, right? So now, if that's a CH3, let's go over here. That's a carbon, yes? Everybody?
Yes.
How many bonds does it need?
4.
So how many hydrogens are on that carbon?
3.
Everybody?
3.
3. It's pretty simple, right?
Yes.
All right, one more time. What about this carbon right here? How many lines from that carbon?
2.
2, right?
Yes.
So how many more bonds does it need? 2. And it's bonded to hydrogens. Is that making some sense?
Yes.
Now, let me draw the next one. The next one will be heptane. C6H16. 7. Thank you. That would be hexane again with too many hydrogens. And then I'd fail. Now, I'm just going to draw heptane as a line drawing and watch how fast and watch how easy it is. I always draw too many though, but let's just see. 1, 2, 3, 4, 5, 6, 7. There you go. That's heptane. Now, I'm going to leave it there for a minute. How long did that take me and how long did it take you to draw that? A minute, a second, right? If it took you more than 5 seconds, you probably were just drawing slow to be neat, right? It's really simple to draw that little zigzag pattern, isn't it? Everybody?
Yes.
Is this a little more plain than this?
Yes.
It is a little more plain, isn't it? There's less to look at. Okay? Now, let's go over this again, because this is an important point. What is right there? What is right here? What is right there? What is right over here? What is that? How many hydrogens here? 3. Everyone agree?
Yes.
How about right here? 2. Why is it 2? Right. And carbon needs how many?
4.
Everybody?
4.
4. Remember that. Carbon only needs 4. Okay? So one more time. How about right here? How many hydrogens?
2.
Everybody agree?
Yes.
2. Okay. This is called the expanded structure. This is called the condensed formula. And this is, well, I'll just do it right here. It's called a line drawing. I call it a line drawing. I think your book might call it a line formula. But I've always called them line drawings. I'm probably wrong. I'm probably line formulas. Whatever the book says is right. But most chemists I know call them line drawings. So that's how you do them. Okay? And I stopped at 7. I'll do one more. I'll get you to 8. And then 9 and 10 just follow from there. It's really simple from that one. Okay? So does everyone kind of get the feel for this?
Yes.
Yeah?
So we're just drawing the zigzag thing, right? Just a line drawing?
If I asked you to draw hexane or heptane or whatever, you just give me a line drawing, I'd mark it right.
Okay.
As long as you had 6 carbons, not 7. What was that?
Now just make sure we don't actually have to write anything else on it.
Depends what I ask you. If I say, give me the expanded structure of hexane, then I'm asking you 2 things in the same question. I'm asking, do you know what an expanded structure is? And can you draw hexane?
Yeah.
You know what I'm saying?
Okay, so
but if I just say, without any explanation, I just say, draw me heptane, and there's nothing else in the question, I would do a line drawing because there's nothing else in the question.
Okay, but if you ask for the expanded and the line drawing, then she'll go.
If I'm going to do that in a question I never have before, little hint, I would ask you for the line drawing, the expanded structure, the molecular formula. I'd ask you for everything.
Oh, okay.
Okay? I'd make it a little bit challenging, a little bit, right? Okay. So is everybody comfortable with this?
Yes.
Okay? Now there's a reason why we're doing all this, and we're going to get to it here in a minute. Let's do octane. You know what? You do octane. You guys do octane. I will give you the formula here right quick. It's called octane. How many carbons must octane have? 8. It must have 8 carbons. So why don't you draw the expanded structure of octane? Well, you know what? Nah, don't do that. That's mean. C8H18. If you can't draw the expanded structure, let me know. I'll deal with that. We can fix that up, no problem. I personally would just draw the line drawing of octane. Just draw it real quick. The most common ways of expressing an organic compound is line drawings or condensed formulas. Most people very rarely write them out as expanded. And I think you can see why. Because they do get very confusing very fast. Okay, we covered a lot of ground there. All right, good for us. There we go. Covered all this stuff. Good for us. Come on now. Come on. Keep going. Keep going. Remote control. Come on, you can do it. All right, we'll stop here. We'll go over a little bit. How'd everyone do? Great! I like that enthusiasm over here in the corner. How about over here? You guys do okay? Everyone doing all right? So, is it hard? No. Everybody else, is it hard? No. No? Good. So let's draw octane real quick and then we'll move on. Octane, I would just do this. 1, 2, 3, 4, 5, 6, 7, 8. That will be octane. I'll draw the condensed formula just for fun. This is octane. Octane. Those are alkanes. These are all forms of alkane. Okay. That's pretty easy, right? Now, write this down. Cycloalkanes. Cyclo means cyclic, or cyclical, or forms a ring. Circle. Well, not really a circle, but they form a ring, for sure. Okay? So now, let's take the simplest cyclic alkane, and that would be propane. The normal structure for propane, C3, CH3, CH2, CH3. That's propane. I think everyone in here is okay with that idea. If I were to draw cyclopropane, the word cyclo, or the prefix cyclo, means cyclic. Means it goes into a circular type pattern. Now they're not circles, but they go into a circular pattern. So that means that you'd have a carbon here, carbon down there, carbon over there, bond it back up to that carbon. So all three carbons make an enclosed structure. So this is the inside of the ring, this is the outside of the ring. Okay? That is cyclopropane. Notice how it has two less carbons. This is C3H6. This is C3H8. Has two less carbons. And that's because this carbon and that carbon make a bond, so you have to lose one hydrogen each in order for them to have room to make a bond. Don't worry about how that happens. It just does. Okay. Propane. That's pretty funny. Pane. There you go. Sorry about that. Propane and cyclopropane. So now let's just go to the next one. I'm sure all of you guys can get this. If I drew butane. Butane is C4H2,3,6,10. That is CH3, CH2, CH2, CH3. And if I were to ask you then, what is cyclobutane? Cyclobutane must be what? Go ahead and give that a try. That will be the formula. What will be the structure? Okay, so try the structure. I'm sure all of you can get a very simple concept, but it's an important one. Because the next two I'm going to introduce to you are very important in terms of humans. Give that a quick try. I'm sure all of you are going to get it. Cyclobute. So the word cyclo means cyclical. Going to form a ring. Raise your hand when you got it. All right, all right. Good job, guys. Very good. Who else got it? Up there? You people over here? You guys over here? Good.
So is it supposed to turn to a square?
Yes! It's a square. You're taking away my thunder, but that's okay. It's going to form a square. I don't mind.
Before CH2.
Yes. In a square. All right, who's got it now? Raise your hand real high if you got it. A few people, good. All right, let's try it. So you have a cyclobutane. Now there's 4 carbons here. So put those 4 carbons into a ring. CH2, 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 bond it together, just like that. And as somebody already pointed out, it's a square. Very good. Now, just like in the other structures, there are ways to draw these as line drawings. And how would you draw cyclobutane as a line drawing? Just draw a square. If you show that to any organic chemist in the world, they're not going to think square, they're going to think cyclobutane. This is how we're wired. Now over here, what's that shape going to be? A triangle. Very good. That's cyclopropane. Okay? That's all there is to it. It's not very hard, right? It's pretty simple. Everybody agree? 2 people do. Okay. So now, if I were to say cyclopentane, what would the structure be? Be a pentagon. Cyclohexane is a hexagon. Now those two, cyclopentane and cyclohexane, are very common in nature. And the reasons why are a little bit advanced for this course. Just think of it this way. Carbons with 4 bonds want to form tetrahedrals. If you have the carbons in a cyclopentane or in a cyclohexane, they're able to form almost perfect tetrahedrals at that point. In cyclobutane and cyclopropane, they're not able to form perfect tetrahedrals. They're actually being compressed a lot, and they don't really like that very much. So these butane and propane are unstable, but pentane, cyclopentane, and cyclohexane Those are quite stable, and they're very, very common. We find them a lot in nature. Okay? Is that all right? How's everyone doing with that?
Can you do one more, like the cyclopentane?
What want me to do? You want me to draw it out?
Yeah, I just want to make sure that I'm getting
Okay.
it correctly.
Sure. You want me to draw out the condensed formula with the CH2s and all that?
Yeah.
Sure, no problem. So, let's discuss this real quick so that we're all on the same page. So here, where two lines come together, that's going to be what right there?
Carbon.
Carbon, very good. What's that one right there?
Carbon.
Very good. And down here?
Carbon as well.
You're awesome. You got it. All right, now, every carbon has to have how many bonds?
4.
Outstanding. How many does that carbon have right now?
1.
Has 2 actually.
Oh, okay, yes.
Left right there, you got 2? So how many hydrogens must it have?
2 more.
There you go. See? You got it. One more time. How many carbons, how many bonds does that carbon have?
2.
And how many hydrogens must it need?
2 more.
Outstanding. You have it. You got it made now. Everybody like that? Everybody else? All right, good. Good question. Okay, so that's the cyclos. So we're okay with that, guys? At least a little bit? Yeah, my little remote got all jacked up. I'm too cheap to buy a new one. I'm not afraid of me. Alkanes with substituents. So we'll go back real quick. Alkanes with substituents. Now, chemistry would be very boring, or at least organic chemistry would be very boring and kind of useless if we weren't able to have different chains. Because right now we're talking about just linear chains of carbons, like one carbon bonded to another, bonded to another, bonded to another, bonded to another, bonded to another. That's exciting if you're in the oil industry, but we want to do more with our organic molecules than just that. So now we're going to talk about alkanes with substituents. Now substituents, we'll define it here in a minute, but just a quick definition of substituent is it's anything bonded to a carbon that is not hydrogen. Anything bonded to a carbon that is not hydrogen is a substituent. Anything bonded to a carbon that is not hydrogen is a substituent. Okay? Now I'll define that a little clearer when we get into it, but for now just think of it that way. It's not quite that simple, but that's a really good way to think about it. Alright, first of all, let's write down the word isomer. Isomer, and for this class, there are different kinds of isomers, but for this class we refer to isomer as a molecule that has the same molecular formula, but a different molecular structure. Now that's weird. Let's draw up an example. Draw an example of isomers. This is the simplest example. C4H10. Now, C4H10, that's butane, right? So we would draw, right now, we would draw this. That's what everyone would draw at this point, C4H10. And you would be right. I would not mark that wrong. But there's nothing saying that it has to look just like that. I'm sorry, that might have been me. That's me, excuse me, I'm sorry. It might not have been me, though. It was, I apologize for that, excuse me. It's off now. I have a wife, you know. She'll tell me she loves me. I love her too. Alright. Now there's nothing that says that these carbons have to be in a linear chain. Nothing's saying that. What if we took that carbon there and put it there? What? Let's draw it. Let's just draw that. Carbon, 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 carbon. How many carbons is that? 4. So it's 4 carbons, right? So I haven't added any carbons. I haven't taken any carbons away. Have I? Everybody?
No.
No. So this is C4, right? So if you're counting the carbons, you would say C4. Let's stick in the hydrogen. This one has to have 3. This one has to have 3. This one has to have 3. Now this one has to have 1. Now you tell me, chemists, does this molecule, excuse me, have 10 hydrogens?
Yes.
And so it has the same number of hydrogens. This one has C4H10. This one has C4H10. Right? Are they the same shape? No, they're not, are they? They're different. They have the same molecular formula, but a different molecular shape. Does that make sense?
Yes.
These two are considered isomers of each other. That's how they're related. This and that are related in that they're isomers. Okay? Isomers. Same molecular formula, different molecular shape. Now this is called butane. This is actually not called butane. And we're going to learn today how you would name this. I'll tell you what the name is right now, and then when we get into it, I'll explain it to you. This is actually called 2-methyl-propane. And right now you're thinking, whoa, where'd that come from? That's a little, I call that foreshadowing. We're going to learn that, how to name them. Okay, it's really simple. It's going to appear to be difficult, but it's not.
So every time we change the structure, the name is going to change?
Yes. But that doesn't mean they're not related. They're still isomers of butane, but they're not both called butane. It's like you're related to your family, but none of you have the same first name, probably. Okay, maybe you're named after an aunt or something, but usually your brothers and sisters have different names, right? Same kind of idea. Okay, here we go. Let's go. Oops. Okay, let's please write all this stuff down. It's actually all very good stuff. Substituents are atoms or groups of atoms attached to the carbon chain that include alkyl and halo groups. Alkyl, halo, what? An alkyl group is a carbon-bearing group. So just any group that has carbon in it. Excuse you. And halo, halogen. Okay? Halo just means halogen. So the halogens are group 17. So these are all halogens here. Okay? They're affectionately referred to as halos. Not the video game. Not the video game. Although that's fun too.
That's the name of that structure? 2-methyl.
Yep. The bottom name is the name of that structure. And you'll learn how to do that here in a minute. And when you talk to your friends, you can start throwing out chemical names and sound really smart. Everyone thinks you're a freaking genius when you put numbers in the middle of names. You know, it's like 5-bromo-4-butadiene. Whoa, he put a number in the middle of that name. Yes, I put 3 numbers in there. Take that.
What was the definition when you were saying it before? Anything that is bonded
To a carbon that is not hydrogen. But this definition gives you a little bit more detail. Okay, because it's the longest carbon chain that you have to worry about. And we're going to get into that in a minute when we get into naming. But I like to give a really simple definition because a lot of students have a hard time with it. And that's why we're going to do a lot of examples so that people can master it for the exam. This will be on your exam. Naming will be on your exam, and it's easy points if you master it. It's easy points. Easy, easy, easy. Okay. So now, an alkyl group, basically any carbon group that's attached to your longest chain, which we'll get into all that in a second. Trust me. Trust me, it's all confusing right now. It will be all obvious when we do examples, I promise. And the alkyl group will end in the suffix YL. Okay? Halo groups. Those are halogens, and you change their name and put an O at the end. So if it was fluorine, it would be fluoro. If it was chlorine, it would be chloro. Bromine is bromo. Iodine is iodo. That sounds funny, but that's what it's called. Okay? Now don't worry, it's all confusing and it's going to make sense here right now. Okay, let's put up the molecule we just had. So that's the molecule we just worked with. And I told you the name of that molecule was 2-methylpropane. Now I'm going to show you how I got there. Now I do these things in my head now because I've been doing them for so long. I'm going to show you a really good, at least I think it's a good system on how to name that. So the first thing you have to do is you have to identify your longest chain of carbons. Your longest unbroken chain of carbons. And I'm going to give you the world's biggest hint. And you might want to write this down. In this class, the longest chain of carbons will be written linearly left to right. It will be written linearly left to right, or it could go right to left. But it will be written linearly along the bottom. I'm not going to try to trick you by hiding the longest chain in a snake-like structure. I'm not going to do that to you guys. Organic 1, I do that to them all day long. You guys, I'm going to make it easier. Okay? Because you're not trying to be organic chemists. You're just trying to learn a little bit. Okay? So now, I just told you that the longest chain will be written linearly from left to right or right to left. So right here, right now, that must be the longest chain. Because I've written it left to right and right to left. So it's written right there. So the longest chain has how many carbons? 3. Right? Everyone see that? The longest chain has 3 carbons. We already talked about what we name a 3-carbon chain. What's a 3-carbon chain called?
Propane.
Propane. There it is. It's propane. Does everyone agree?
Yeah.
Now you may not have known that right now because you haven't learned it yet, but it's in your notes, in your book, you'll learn it. It's propane. So what I would do is I would write the word propane right here. So no matter what you do, the name of this molecule is going to end in propane. Okay? The end of this word, name is going to be da-la-la propane. We don't know what da-la-la is yet, but it'll end in propane. Okay? Now, the next step is going to appear to be nonsensical, but trust me, it's going to make sense. Take a different color pen and number your carbons from left to right like this. 1, 2, 3. Doesn't make any sense yet, just do it. Now take a different color and number it right to left. Don't worry, just do it. 1, 2, 3. So just do that. Trust me, it will make sense. Okay? That's all I want you to do. And we're going to do a harder example than this, I promise. This is a very simple example. We're going to do harder ones here in a minute so you can get the feel for it. Okay? Okay, so now, looking at your carbon numbers, the blue numbers only. Hanging off of this chain, hanging off of these 3 carbons, looking at this carbon here, is there anything hanging off that carbon that is not hydrogen? No. Don't worry about that carbon, because that carbon is here. The word propane takes into account these 3 carbons. Okay? So we already know these 3 carbons are here. So there's nothing on that carbon that is not hydrogen. Is that correct? Yes. Everybody? Yes. Everybody else? Yes. Yes. Now, so ignore that one. Don't even worry about it. Go to carbon blue number 2. Is there anything on that carbon that is not hydrogen?
Yes. Yes.
Who says yes? Yes. Who says no?
We don't know.
We don't know. That's a good question. There you go. We don't know. Well, if this was just propane, if it was just propane, let me draw propane. That's propane, yes? Okay, everyone agrees with me that's the structure of propane? Everybody on the same page now? So I look here, CH3, I come over here, CH3, right? Here, I have 1 hydrogen and this CH3 thing coming up here, right? Everybody on the same page? Yes. Everybody? Yes. Over here, what do I have there? What do I have here? So it's different, isn't it? Yes. Carbon 2 is different, is that correct? Yes. Everybody? Yes. In the back? Yes. All right. So there is something on that carbon that is not hydrogen, is that correct? Yes. there's this CH3 thing here. Is that correct?
Yes.
Everybody? All right, let's deal with that right now. There's a CH3 there. CH3. Now, that's a little bit of a problem. What are we going to call that thing? We got to give it a name. We got to tell the reader what's hanging off of that carbon, and it's CH3. Well, what you do, and it's very simple. You look at the number of carbons, and you say that's one carbon, right? What's a one carbon hydrocarbon? Or alkane, excuse me. What's a one carbon alkane? Methane, right? It'd be methane, right? One carbon would be called methane, right? But now this is not methane. It's hanging off of another molecule. It's dangling out there like an appendage. So you can't call it methane. Because if you say methane, everyone's going to think CH4. So it's not methane. You change it to methyl. The YL, right? So it's saying this is called methyl. M-E-T-H-Y-L. The YL is very important. It tells the reader it's hanging off of another carbon. It's hanging off of my longest chain. It's a substituent. If you don't put the YL in there and you call it methane, I'm going to think you're putting a CH4 there. You follow what I'm saying? I know it's weird, I know it's subtle, but that's what we do. Okay? Organic chemistry, a lot of people call it another language. It really is a second language. You know, we have all these little rules that you have to follow. Okay? So you wouldn't call it methane, it's methyl. Does that everyone kind of follow that a little bit? Everybody? So let's do another example. This is not on the molecule, I'm just doing an example. If we don't have this, but if we did, if we had this hanging off of our longest chain, if that was hanging off of our chain, it's not, but if it were, there's two carbons there, right? Everybody?
Yes.
Two carbons is called ethane, but it's hanging off of a longer chain of carbons. So it would be called ethyl, right? You see how this is working? If it was three carbons, what would it be called? Propyl. Propyl. 4 would be butyl. 5 would be pentyl. 6, it gets weird at that point, because normally you won't have 6, but usually you'll have 1 or 2, maybe 3. Okay? Methyl, ethyl, propyl. Okay? Those are substituents. They have to be hanging off of a larger carbon chain. So far, so good? I know that's a little confusing. I know it is. But stick with me. I promise you we'll make it logical. At least logical enough that you can go home and practice. Okay? Okay, so that's called methyl. So let's just point to it. Methyl. That's called methyl. Now, using the blue ink, and don't worry about the black ink just yet. The blue ink. What carbon number is this? 2, right? So it's 2. So we would write right here, 2 dash. The dash has to be there. 2 dash methyl. 2 dash methyl. The 2 is the address. That's where the methyl lives. The methyl lives on carbon 2 according to the blue ink. Okay? Everyone follow that? 2 dash methyl means the methyl is residing on carbon 2. So far? Everybody? Now if we use the black ink, it would be 2-methyl again, wouldn't it? You would just say 2-methyl one more time. Now that seems nonsensical. For this simple example, it is. But what you have to do is you have to find your substituents and find the number that the carbons are on, number them left to right and right to left. Okay? And then what you do is you write them down like this. So I have 2-methyl and 2-methyl. If the numbers were different, say it was 3 and 4, just for example, you would pick the lower number. Okay? Use the numbering system that gives you the lowest number. In this case, they're both the same, so it was nonsense. But in a lot of cases, like the one we're going to do next, it is not nonsense. Okay? So no matter what we do, no matter how we number it, the methyl group is on carbon 2. Does everybody follow that? Everybody?
Yes.
Okay.
So the name of that is 2-methyl?
2-methyl propane. What's that? Okay. Now, you would write it like this. 2-methyl propane. Numbers and letters are separated by dashes. You have to have the dash there, because numbers are separated from letters by dashes. And this, all one word. That is to say, there's no space there. Okay? Methylpropane is all one word. 2-methylpropane. That's how you name that. Now, does that seem like a mystery? Does it seem mysterious how to do this? I mean, when you saw the name the first time, you were probably thinking it's a little strange, but now it's a little bit less mysterious, right? Go ahead.
Probably a dumb question.
Probably not.
You only focus on the top letter, not the ones on the side.
What do you mean?
The methyl, CH3.
Because that was the only thing that was hanging off of my longest chain. No, remember the longest chain is from left to right or right to left? That's a great question, actually. Whenever you find the longest chain, and in this class it'll always be written along the bottom, left to right or right to left. When you find the name of that, that name takes into account all the carbons in that chain.
Okay.
You see what I'm saying?
Yeah.
So that's why the methyl on the left and the methyl on the right, we didn't worry about them because they were part of the chain.
Oh, so anything off of it, either.
Yes,
top or
exactly.
bottom.
Anything hanging off of the chain, we worry about.
Okay.
Because what we're trying to do is describe to a reader how to draw this molecule. Okay? And believe it or not, if you took the name 2-methylpropane and gave it to a non-English speaker, say someone from Iceland, they could draw that molecule if they were a chemist. Easily. They could do it easily. Okay? That's why we're doing this. Okay, go ahead.
When you say 2 carbon, did you look on the top or on the...
I looked along the left, from left to right and right to left. The longest chain will always be written from left to right or right to left. Always.
Well, we need a 2 where the 2 comes from.
Yes, exactly. The 2 comes from the fact that 1 carbon, 2 carbons. And if we go from the right, it's 1 carbon, 2 carbons. So no matter which way you number it, you get the same numbers. I'm going to show you an example here in a hot second that you don't. Okay? Well, this is how you should do it. All right, very good question. Anything else?
Just one more.
Go ahead.
And you named it the methyl because it's only that one.
1 carbon.
Connector. What
Yep.
if there was 2?
Be ethyl.
So it'll just change that way. Right?
Yep, because 2 carbons is ethane. If it's hanging off of a longer chain of carbons along the bottom, you call it ethyl.
Because it'll be 2 sticking out.
It's 2 carbons.
Okay.
Yeah. But now, we'll get to another example that I think will help you too. Okay? I promise. Anything else? All right. Let's draw another carbon out. Let's draw another example. One more time, as they say. Now, whenever you don't feel comfortable with a problem, the solution is not to quit. The solution is to do more problems. And if you're having trouble, come and see me. I will get you through it. It's really not hard. Okay, let's try this one. Carbon, 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 carbon. Let's put a CH3 here, a CH3 there, and we'll put everything else like this. All right. Now, again, I promise you, I will always put the longest chain from left to right or right to left. So how many carbons are there in my longest chain? 5. And what's that called? Pentane. Very good. So no matter what we have as a name, it's going to end in pentane. Okay? That's going to be the ending of our word, of our name. So now, what do we do next? There we go. 1, 2, 3, 4, 5 in red ink. And 1, 2, 3, 4, 5 in black ink. Now there are shortcuts to this. Your book describes one. If you want to do it that way, I have no problem, as long as you get it right. My way will get it right every time. It might take you a little longer, but it'll get it right every time. The book's way will get it right every time if you follow the rules correctly. in my experience, the students don't follow the rules correctly. So I've invented this little procedure. It's longer, but it always works. Okay, let's consider the red ink and the red ink only. Don't worry about the black ink just yet. If we look at carbon 1, are there anything hanging off of this carbon that is not hydrogen? No. How about that one?
Yes.
Ooh, what do we got?
CH3.
Which is called?
Methyl.
Methyl. There it is. So 2-methyl. Alright, so we found one thing. That's awesome. Here, CH3, carbon number 3, we have another methyl. There's 2 of them. That's complicated. Okay. 3-methyl. Carbon 4. Yeah, just hydrogen. Nothing serious. Carbon 5. Yeah, hydrogen. Yeah, whatever. Nothing serious, right? So that's the red ink. Let's get the black ink out now. Let's check that out real quick. So going from the black ink, that's carbon 1. Nothing happening. Carbon 2, using the black ink. Nothing. Carbon 3 now.
Yes.
Methyl, right? So we got to write 3-methyl. And carbon 4, another methyl, right? Everybody with me? And carbon 5 is just a bunch of hydrogens. The black carbon 5, just a bunch of hydrogens, nothing serious. Okay, now we have to think. The red ink, we have 2 and 3. The black ink, we have 3 and 4. What numbers are lower? 2 and 3. Those are the numbers you want to use. You do not want to use the bigger numbers. Okay? Does that make sense? Everybody good with that? Alright. So what I would do if I was on an exam, I would not scribble that out. I would not erase it. I would simply put one line through it. Just like that. Why? What if you pick the wrong ones? What if you make a mistake and you have the right numbering system, but you pick the wrong one and you obliterate one? Now you got to do it again. If you just put a line through it, you can still read it, right? I can still read it. I can still see that you had it, you just made a mistake, and instead of getting 2 out of 10, you get 9 out of 10. See what I'm saying? Leave your stuff there. If you erase it or you obliterate it, I can't see it. If you just draw a line through it, I can still see it. Okay, so now, we have 2 methyls to deal with. Isn't that exciting? A few people think so, right? I think this is pretty cool. Now, we have to deal with that. There's 2 methyls. Well, we could say this. Let's write this out. I'm going to write it out incorrectly first, and I'll show you how to write it correctly. So write down the incorrect way first. You could say 2-methyl -3-methyl pentane. And then draw an unhappy face. Like that. He's really sad. Because that's not right. Now, I drew that up there so we could look at it. If you were inventing a naming system, would you write this 2-methyl -3-methyl pentane? Does that even flow off the tongue nicely? It doesn't, does it? It's kind of like, there's got to be a better way than that, right? In fact, there's a much better way than that. Here's how you draw it correctly. Or write it correctly. Let's draw it in black. 2, 3 dash. Numbers are separated by commas. 2, 3 dash. This is telling the reader that at carbon 2 and carbon 3, something really cool is going to happen. You haven't said what yet, but something's going to happen. Be ready for it. Carbon 2, carbon 3, something cool is going to happen. Now, how many methyls do we have? How many are there? 5. Who said 5? How'd you get 5?
No, I was just saying, I thought
you're adding the 2 and the 3.
Methyl.
That's good. That's a common error. That's why I want to know who said it. You're making common mistakes and you're going to get it right on the exam, so you're going to be fine. The reason why it's not 5 is those are not amounts, those are addresses. One methyl lives at carbon 2, the other methyl lives at carbon 3 on the same street. See what I'm saying? So they're not amounts, they're addresses. Think of them that way. Good, good. You're not the only one, trust me. This is the bravest one. Good for you. Now, at carbon 2 and carbon 3 we have methyls, right? So there are 2 of them total. How do we say two in English? You have two things. Die. Right? Two things are die. Make sense? So you'd say dimethyl. Make sense? How do you say three? Four? Gotcha. Tetra. Dimethyl pentane. And this one, put a check mark and a happy face.
So you choose di because like the lowest.
Because there's two of them. You have to say dimethyl. The reason why is, I don't really know why, but I can only imagine because people who invent this stuff are Swiss German. They're very exact, which is why their watches are so good. So they write a system that has redundancy built in. So you say 2, 3. So you already know there's going to be two something. And then they say dimethyl. That way that the reader knows there should be two things. And then the dimethyl comes in, there are two things. So the system itself will check itself. So there's two here and two there.
3 and 4 will be trimethyl.
Yep. Wait, no, 3 and 4, no, it will just be di again. Because there's still only two methyls. If there was 2, 3, 4, then there'd be 3 methyls, it'd be trimethyl. Got it? There it is. Good. See?
So if you just cross out the black ink,
Yep.
the 3-methyl and 4-methyl,
Yep.
why would you even write it out if you're only going to use the red methyl?
You're trying to figure out which way to use it. You don't know which way is right until you write it out. Unless you can find the trick. Now there is a shortcut. I don't talk about it because it confuses the heck out of people. If you have your own way that works for you, ignore everything I just said.
Okay.
As long as you get the right answer.
So you write out the numbers 1 through whatever,
Yep.
and then from left to right 1 through, and then you see where it,
See where you get the lowest numbers.
okay,
You always have to have the low numbers.
okay. So what if you had 2, 3, 4, 5? How do you know, like, to always use just the 2 lowest?
You always use the 2 lowest, no matter what happens.
But how do you know to not use the 3 lowest? Is there ever going to be a 3?
Yeah, if there was 3 numbers, it would be the 3 lowest. So you may have 2, 3, 4, or 3, 4, 5.
So you just don't use the highest number?
You never use the highest.
So anything below the highest number, if there's 5 different numbers?
Yep,
you
just use the lowest one.
Okay. Gotcha.
You know, we won't even get to those complicated
Okay.
ones. 3 is where I'll probably max up.
Okay.
Okay? I'm not gonna try to trick you.
Okay.
They're gonna be straightforward examples.
Okay.
I mean, there's numerous ways I can trick you, and that's no good to me or you, so I would never do that. Is that good? Like, I'll never try to trick you, so don't ever trick yourself?
Yeah.
Students do that. Like, I don't have to try to trick you. You will trick yourself. You will overthink problems, and you will say weird things because you're thinking way too deeply. Okay, so everyone's kind of confident now, right? Let's do, there's probably a learning check here somewhere. Let's do it. Find one. Okay, let's do this one. Let's do this one together. Well, you know what? Yeah, let's do it together. It's a little bit hard. Okay, so that's a common exam question. Not this exact one, but one with that difficulty. So how many carbons we got there in the longest chain? 4. Along the bottom there are 4. So what is that? It's a butane, right? So no matter what we do, we're going to call this a butane. So let's go ahead. I like to draw the structure out myself, so let me just do that. And one real quick thing, it does not matter if the bromine's down or the bromine's up. It doesn't matter. Makes no difference. Carbon, CH3. Let's try this one together. This one has some nuances to it that I want to show you as well. So I'll do it with you. Now, we know that's a butane. So let's just write the word butane right here. Okay, so no matter what, the ending of our name will be butane. Sound good? Okay, let's number left to right and right to left. Unless, of course, you found yourself a shortcut. You can keep that to yourself, please, because I don't want to confuse people. There you go. Left to right and right to left. Okay. Everybody's happy, right? Now, ready? let's just start with the red ink first. On carbon 1, using the red ink, what do I have on here that's not hydrogen? Bromine. So you got to say 1-bromo. What's on carbon 2? Bromo. 2-bromo. And 3? There's a methyl, right? Everybody see it? Yes. So it'll be 3-methyl. All right. And that's all that's there for substituents using the red ink. Now, I'll switch to my blue ink. Now, again, once you get used to this, you'll probably see there's a few shortcuts you can take. By all means, if it works, take them. If you can't figure that out, do it this way. It's not that bad. Now, the blue ink, carbon 1. Not a lot going on at carbon 1, right? Carbon 2 of the blue ink. What is there? Methyl. So it'll be 2-methyl. And carbon 3 of the blue ink. Everybody? Yes. Using the blue ink only. Carbon 3 has a... Everybody. There it is. Carbon 4 is a bromo. All right. Now examine the numbers. Pick the column with the lowest. Which one has the lowest number, the red or the blue? The red, right? Because red has a 1 in it, right? Everybody happy with that? Yes. Take a line, single stroke through the blue. Do not scribble it out. Do not obliterate it in case you're wrong. Sometimes you choose the wrong one just because you're rushing. Don't scribble out your information. Okay, so that's cool. We've got that done. We have our lowest numbers. We're going to use the red. But now we got something to deal with here. We got two different substituents. We got methyl. We got bromo. Now you throw your hands in the air. Which one comes first?
Bromo.
Why would bromo come first?
Because you need the prefix like di or tri.
Oh, that's not a bad way to think of it, but it's even easier than that. It's even easier than that. What comes first in the alphabet, B or M? B. B. Bromo comes first because it's alphabetical order. Now, there's two of them. So you're going to have to say dibromo, right? Yeah. You ignore the di. When you're putting them in alphabetical order, ignore the di. You go with the B. Okay? So if it had been, say, trimethyl, or so tribromo, so the T is after M in the alphabet, you would ignore that. You would use the B. You follow me? It's always the letter of the substituent, not the suffix. It's always the substituent. So bromo comes first. Follow that?
Is it only for bromo?
Nope, always alphabetical. Everything's alphabetical. The substituents always go alphabetical. And the name of the longest carbon chain always goes at the end. So always put them alphabetical. Okay? Make sense?
Yep.
Everybody? So if there was a chlorine in here, say bromo and chloro, it would be bromo first, then chloro, because B, C. Is that okay with everybody?
Yes.
All right. So this name would be 1, 2, dash, so 1 and 2, dash, dibromo. So now we've taken care of this and that. Then it will be dash 3 dash methyl butane. There you go. So now 1, 2 dash dibromo dash 3 dash methyl butane. Okay? Now, if you want to sound super smart, say that. People will think you're a genius. Not really. They'll just think you're a nerd. But still. Depends on what kind of, lifestyle you want to portray. Lifestyles of the weak and nerdy. All right. Is that hard? No. That's about as hard as they get in this class. Now, if this is organic 1, you wouldn't believe when I throw at those guys. But that one is about as hard as it'll get. Okay?
Can you explain how did you get the di again?
There's 2 bromines in the molecule, yeah? Mm-hmm. So you have to tell the reader not only the numbers, 1 and 2, or 3 and 4, wherever they live, but you have to also indicate that there's 2 of them, so you say dibromo. The reason for that is there's a redundancy built into the naming system, because the 1, 2 tells you that 2 things are coming out, right? Tells you there's 2 things on those. There's one substituent on carbon 1 and 1 on carbon 2. But then you say dibromo, because you're telling the reader there's 2 things coming and there's 2 bromines. Dibromo. It's redundant, but it has to be there.
So for that, you could tell from the structure too, right? That you have 2 bromine.
That's where we're going next. How do you get a structure from a name?
So let's say, okay, I get you use the dibromo because there's 2 bromos. So let's say if you had 2 methyls on top of that, would it be like the dibromo and then the dash 3 comma whatever the other number is, and then dimethyl?
Let's do it. Let's just do it. It's a great question. Let's just do it. I'm going to change the question. Okay, so we'll redo it. It's a great question. I'm going to take that hydrogen away, and I'm going to put a methyl right here. Okay? Everybody happy with that? I just took the hydrogen away and put a methyl there. So it's a different question now. So it's still butane. Still butane. Actually, let's make it even more different, just for clarity's sake. If I had left it that way, there's another subtlety I never told you about, and you don't learn in this class. So we made the carbon chain 1 carbon longer too. So now it's a pentane. Okay? So now we have another substituent we have to deal with. So we number from left to right. 1, 2, 3, 4, and 5. And 1, 2, 3, 4, and 5. Let's go. I'll do this a little quicker now. I think everyone's kind of on the ball here. It will be 1 dash bromo, 2 dash bromo, and this would be 3 dash methyl, 3 dash methyl. I wrote it twice because there's 2 of them on the same carbon. That's all it means, just 2 of them on the same carbon. Now, the red marker, it would be 3 methyl, 3 dash methyl, 4 bromo, and 5 bromo. Right? Does everyone kind of agree? So the red ink is no good because it's got too high numbers. This one's the one we use because it has a 1, 2. Yes?
Yes.
Now the question was, how would you name that? And that was a great question. How I would name that would be like this. I'm going to erase the red so I can write it right here. On an exam, you would leave the red there. Let's just name this real quick. It would be 1, 2 dash dibromo. Okay? Dash 3, 3 dash dimethyl. Pentane. I put the 3 there twice because there's 2 substituents on carbon 3. So I know it looks weird, but you have to put the 3 there twice. And then you say dimethyl. Okay? If there had been 3 methyls, you would have said trimethyl. Does that make sense? Go ahead.
So the numbers come from when you draw it out, like how many you have.
The numbers come from the carbon number. You number left to right, or right to left, and the carbon 1, carbon 2, carbon 3, carbon 4, carbon 5.
And then the di comes from how many do you have?
How many substituents you have. How many of the same substituent do you have? So if you had 3 bromos, it would be tribromo. If you had 1 bromo, it would just be bromo.
Where did the second methyl?
There's 2 of them on the same carbon, so they're right here. Right? So you have to say 3 twice. Because you have to, the first number indicates one of the methyls is on carbon 3. The second 3 says the second methyl is on carbon 3. It just happened to be on the same carbon. It could have been 3, 4, and put the methyl on the next carbon. All right? How we doing, guys? It's not tough, is it? It's a practice. You just got to do it a couple times, and you will be golden. All right, let's get to some different kind of problems here. Okay, draw the structure from the name. So So now we have a name, and I want to draw its structure. The easiest way to do these problems, and these problems are really simple. These problems are dirt easy. You look at the end. You look at the end, and you say 1-chloro, 1,2-dimethyl heptane. How many carbons in a heptane? 7, right? So what do? Just draw 7 carbons in a linear chain. Seriously, it's that easy. Watch this. You're going to be amazed. And you're going to be like, wow, that's pretty cool. Because it's so simple. So I'm going to take my marker. Here we go. 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons in a chain. Now, I would just number my carbons left to right. Because you don't have to number them right to left. Just left to right. That's good enough. 1, 2, 3, 4, 5, 6, 7. Now, read the name. 1-chloro. What does that mean? There's 1 chlorine. Where is it? It's on carbon 1, or the first carbon. Very good. So we'll put a chlorine. It doesn't matter. Up, down, left. Doesn't matter. I put them up because it feels good. Could have been down. Doesn't matter. 1 chlorine. Now, what do we got here? 1-2-methyl dimethyl. So what's that mean?
There's 2 methyls.
There's 2 methyls, and they're on carbon 1, carbon 2. There you go. What else we got? That's it. The rest are hydrogens, exactly. Now, let's go through that exercise real quick. How many hydrogens must be on that carbon? How many hydrogens are on that carbon? This one right here.
1.
1. Who said 1? Raise your hand. Outstanding. Raise your hand real high and say, self-high five. There it is. Good job. She did right. She's right. How did you know that?
Because there's supposed to be 4 bonds on carbon and there's 3.
Subtraction, right? 4 minus 3 is 1. So there's 3 bonds to the carbon, as she said. So the other bond must be hydrogen, right? If it's not indicated, it must be hydrogen. Very good. So there's a hydrogen here. How many hydrogens on carbon 2? 1? Everyone agree? Yes. It's 1. Very good. How many hydrogens on carbon 3? 2. And carbon 4? 2. Carbon 5? Carbon 6? And carbon 7? 3. There you go. And that's the answer. Okay? Was that hard? That's easier than naming from a drawing, I think. But pretty cool, right? See, there's another example. We'll do 2 of them here. If there's another
So
one.
it's always from left to right when
you draw it from the name, yeah. It makes, you could do it from right to left if you wanted to, but that's counterintuitive. Most English writers write left to right, so I just say do it that way. You can even do it up and down if you want it, but that would be really weird. You could do it though. Okay, let's draw this one together. Draw the condensed structural formula of 3-bromo-1-chlorobutane. Give that a quick try again.
You will never ask us to write the condensed formula for that?
I probably would just ask you to draw the structure. If you draw the condensed and it was correct, I would mark it, right?
I mean, the condensed, what I did, for example, in the first one, I count how many carbon and those carbon 2,
Yep.
H4Cl.
Well, that's not the condensed, that's the molecular formula. Condensed would be CH3, CH2, 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 CH3.
Yeah, but
That's expanded. Huh?
But how is it in the condensed formula, the substituents?
We'll see right here. You could write that as expanded if you want right now, that's fine. And we'll do condensed here in a minute.
Okay.
It's easy, don't worry, it's easy. All right, raise your hand when you got it. A lot of guys got it. Good, very good. So let me just draw it up real quick and we'll take our break and then we'll come back and we'll finish what we can in chapter 10. So it's a butane, so that's going to be 4 carbons, right? So there's our 4 carbons. 3 bromo, so there should be a bromine here. And 1 chloro, so there should be a chlorine here. Now it says condensed structural formula, so we have to be mindful of that. So this should be H3, H, H2, and H2. Let me make that a little cleaner now. Okay? That's a condensed structural formula. And the substituents are just drawn in. Bromine, chlorine, just like that. All right, I'll see you guys back here in 10 minutes. Everybody agree? It's been about 10 minutes? Ruled by consensus. All right, properties of alkanes. Now, in our society, we have lots of alkanes, believe it or not. Starting with the lightest ones. Methane, ethane, propane, and butane, those are generally used as heating fuels. You just burn them, basically. Basically, those are the key components of natural gas. So that's what we burn in our furnaces in the north. Of course, down here in Florida, we burn them for barbecue. We burn them for fun. In the north, they burn them to exist, just to survive. Alkanes 5 through 8, the higher molecular weight ones, the bigger ones, those are volatile liquids at room temperatures. What does that mean? Volatile liquid means they evaporate quick. That's basically what it means. And they're also very flammable. So we use them usually as fuels, motor fuels, gasoline made from octane and other isomers of octane. And they get bigger from there. As they get bigger, we use them for things like kerosene, diesel fuel, stuff like that. Okay, so just write down a few quick points here. Nothing too serious. Small molecular weight ones are heating fuels. The mid-sized ones are motor fuels. These things right here. Those are generally. Okay. All right, so those are motor fuels, and then oops, sorry. Then the mid-rate, the little heavier ones, 9 through 17. That's your motor oils, mineral oils, kerosenes, diesels, jet fuels, something like that. The bigger ones. And then these are just real quick points. These are in your book, so just please read your book as well. I really need to get through the stuff, the more important stuff. Alkanes of 18 or more carbons, those are your big ones, those are waxes. And they use them to coat fruit, believe it or not. To help your fruit not bruise so easily in the supermarket. Funny thing that I've always thought was odd, especially if you live in Michigan. Michigan's a big apple producing state. Apples in Michigan are dull color, they're not very shiny, they're just kind of dull, you know. And then you go to the store and buy the apples, they're like shiny like a car. And I'm like, well, that's weird. Turns out they wax them and polish them to make them shine. So that you'll buy them. Isn't that fun? Of course, alkanes are not polar. They won't dissolve in water. They're less dense than water and they're flammable in air. So for example, motor oil is not as dense as water. So it will float on top of water. It's not soluble in water, so it won't dissolve in water. So when you go to the grocery store and buy yourself some salad dressing, you'll notice the oil floats on top, the water sinks to the bottom, and they don't mix. You have to shake them to emulsify and put them on your salad. Okay? Oil and water don't mix. That's a little old proverb, and it's still true today. All right, let's get to the more important stuff. Functional groups. Functional groups. Now, write that word down, functional groups. Also write down classes of compounds. Hey, you got it up there, nice. Yeah. Was that you?
Yeah.
Thanks.
Took a minute to think of that.
Well, you weren't under any stress, right? But you were on tape. We got all that on tape. If you fell down, hopefully you didn't. Now, organic chemistry would be boring and useless if it was just a bunch of carbons. But now we're going to start throwing in other atoms, like oxygen and sulfur and nitrogen. Those things can do things. They can make the organic molecule, first of all, soluble in water. Second of all, they can do things like add flavor or smell to compounds. Really? Flavor or smell? Yes. Flavor or smell. I like this slide for one reason and one reason, well, for numerous reasons, because it shows you you know, like vinegar has a nice smell, bananas have an obvious smell. But now, after the whole Breaking Bad thing, there's a little methylamine right there. So those of you who watch that show, you know that methylamine is what they use to make their drug with. I always thought that was funny. Because I love that show, by the way. I think it's a great show. Methylamine is a gas at room temperature. And they're lugging it around in a big 2-gallon barrel. That doesn't make sense to me. Gases are in cylinders usually. One episode, if you listen very carefully, they mention that it's a solution in water. They actually do mention that. I was listening for it, but I was laughing at it. But anyway, I'm a nerd. What can I say? So now, functional groups provide smell, flavor, and biological function. Functional groups will behave. Let me see if I can get that slide. Come on now. Come on. Here we go. I guess we're buying a new one on Amazon this week. Organic molecules, carbons have 4 bonds. Sometimes oxygen, nitrogen, sulfur, fluorine, chlorine, or bromine. Those are functional groups. They're adding functionality. Go write this down. I'm flipping right now. Come on. Come on. Come on. All right. Well, this isn't going to work. We're going to buy a new one. Oh, we changed. They don't buy these for me, by the way. I buy these myself. These are expensive. It's like $50 for this sort of thing. There we go. Functional groups are characteristic feature of molecules that behave in a defined, known fashion. So if I have a functional group saying alcohol, I can tell you how alcohol is going to react because they all kind of behave the same. Now there's nuances for bigger and smaller ones, but they all kind of behave the same. They're composed of atoms or groups of atoms that are not usually carbon and hydrogen. Not usually. And they replace the hydrogen, and they're classified in families of organic compounds. Okay? So the families of organic compounds. And what I want you to be able to do is be able to identify a family of compounds by sight. So if I show you a family of compounds, you'll say, that's a ketone. That's an aldehyde. That's an amine. I want you to be able to do that. Why? Because it will help you as you go forward into the other classes that you're going to take, like micro, and if you get any kind of nutrition or any kind of metabolism courses, this will help you. Okay. The first family of compounds we're going to talk about are the alkanes. You've already seen them. We just talked at length about them. Any family of compounds that has carbon bonded to carbon and all it has is hydrogens. So carbon and hydrogen only. Carbon, let's do it this way. Carbon to carbon single bonds only. Carbon-carbon single bonds only, plus hydrogens. Plus hydrogens. So there's only carbon-carbon single bonds and the hydrogens that fill in the spaces around it. Those are alkanes. So this is an example of an alkane. That's ethane, as you guys already know. That's ethane. That's a class of compounds. The alkanes. Alkanes. Only carbon and only hydrogen. And only carbon-carbon single bonds. Now we also have another class of compounds, another family. They're called alkenes. Alkenes. E-N-E. Ene. Alkene. Alkenes, here's an example of one. Alkenes have at least one carbon to carbon double bond. At least one. They must have at least one. And the rest are hydrogens. Well, the rest could be actually more than just hydrogen. We'll just leave it like that. This is ethene. Or ethylene. We need either way. Ethene or ethylene. It's an interesting compound. You've all smelled it, believe it or not. Probably, I shouldn't say you all have it, you probably smelled it. Do you ever have apples in your little drawer of your fridge and pull it out and smell that little odor they give off? There's the apple flavor odor, but then there's a little odor. If you don't know what it is, you probably couldn't identify it, but I know kind of what it is. That's ethylene. Fruit give off ethylene molecules as they ripen. And what they do is they cause other fruit in the vicinity of them to also ripen. Which is why if you've ever heard the expression, one bad apple will spoil the barrel, that's because that one rotting apple is giving off tons of ethylene, telling all the fruit around it to ripen. Have you ever noticed on a banana tree, as soon as one banana ripens, they all ripen within a couple of days? Because one banana is giving off ethylene, signaling all the other ones it's time to ripen. The old trick, you have a banana that's not quite ripe, put it in a bag with an apple, it'll be ripe the next morning. That's because the apple is giving off ethylene. And the banana goes, oh, time to ripen. Ripens. It takes a day or so.
You separate your fruit, will it last longer? Or?
Yep, should. Like when they store fruit, they actually pump nitrogen over the fruit to pull off the ethylene so they won't ripen. Neat, huh? Alkynes. Alkynes. Y-N-E-S. That's not very neat. Let me do that again, sorry. Carbon to carbon triple bond. At least one. Carbon to carbon triple bond. This one is acetylene, so I won't even try to spell and embarrass myself. It's called acetylene. That's what they use in welding torches. So it has a lot of energy in that triple bond. You burn it, it gives you a ton of energy, and it allows you to do some welding. Now, in general, these classes of compounds have only carbons and hydrogens in them. Now they could have others, but in general they don't. So any molecule that contains only carbon and hydrogen, so if a molecule contains only carbon and hydrogen, those molecules are called, this is a collective term now, hydrocarbons. If your molecule contains only carbon and hydrogen, they're known as collective, big broad term, hydrocarbon. Okay? Hydro for hydrogen, carbon for carbon. Hydrocarbon. Okay? Make sense? Yes. Alright, so those are three classes. Alkanes, alkenes, alkynes. Single bonds, double bonds, triple bonds. Alkanes, alkenes, alkynes. Not too bad, right? Let's talk about our first non-carbon family. How about this one, the alcohol? When you have a carbon bonded to an OH, this is an alcohol. Carbon bonded to OH. And on here, these can be hydrogen or carbon. H or carbon. So you can have all kinds of stuff there. Now, an example of that is that. That's ethanol. That's called ethanol. That's what's in beer, wine, and all the alcoholic spirits. That's what makes you feel happy good, 10 feet tall and bulletproof. And it also makes you feel like you wish you were dead the next morning. That's ethanol. Now, an interesting cousin of ethanol is methanol. Methanol. This one will put you in your grave. That will kill you. This one will make you feel really tough for a while. Now, notice methane. M-E-T-H-A-N. That means one carbon, right? One carbon. Ethane means two carbons, yeah? 1, 2 carbons. See how it all fits together? Pretty neat, huh? So those are the alcohols. Ketones. Oh, let's do one. I'm sorry. Sulfides. Thiols. Thiols. I guess the book calls them thiols. Thiols. Well, those are very similar to alcohol, except for sulfur. Oxygen is replaced by sulfur. So those are called thiols. And those stink really bad. They just do. Okay? Those are thiols. Thiols and alcohols are very similar, except for it has the sulfur instead of the oxygen. But there's a carbon, sulfur, hydrogen. Alcohols are carbon, oxygen, hydrogen. Okay? See the similarities? But they're also different. This one doesn't smell. This one stinks really, really, really bad. Most of them stink. Not all of them, but most of them. What else we got? Okay, ketones. Let's do ketones now. Ketones. Carbon bonded to carbon, bonded to carbon, double bond to oxygen. We'll stop here for a moment. The carbon double bonded to oxygen is a very common structural element, let's call it for now. They're known as functional groups. That is actually a functional group. Now these, alcohol is a class of compounds. Hydroxyl, we didn't talk about it. This is called hydroxyl. Don't worry about that. That is a functional group. Here, this thing is called carbonyl. Carbonyl. Carbon double bonded to oxygen. Doesn't matter what's hanging off of it. Carbon double bonded to oxygen is called carbonyl. Okay? So whenever you see a carbon double bonded to oxygen, that's called carbonyl. Now, if on the left and the right hand side of a carbonyl are carbons, that's a ketone. Okay? So we have our carbonyl right here. Carbon here, carbon there. That's a ketone. An example of a ketone. Oops. That's called 2-propanone. Prop. P-R-O-P-A-N-E. That's propane, right? How many carbons in that? 3, right? 1, 2, 3. 2-propanone. You guys know it as acetone. That's what it's commonly referred to as. You all know what acetone is, right? Nail polish remover. 2-propanone is the chemical name. Common name is acetone. Now, I'll be honest with you. I've only heard one chemist in my life say 2-propanone, and everyone laughed at him. We call it acetone too. It's ubiquitous. Everyone calls it acetone. Nail polish remover. And if you want to have access to a good source of nail polish remover, marry a chemist. Because I'll get you all the acetone you need, honey. That's what I bring to this relationship. Hey man, I'm telling you, the stuff you buy at the store, the nail polish remover is watered down or something. It's not very powerful. Okay, what else we got? Aldehydes. Aldehydes. There's a big word. Aldehyde. Wow. If you want to sound really snooty when you're drinking wine, say, it has a very aldehyde aroma. Oh, it sounds so stupid, doesn't it? Especially because you know they don't know what they're talking about. Aldehydes look like this. You have a carbonyl and a hydrogen bonded directly to it. That's an aldehyde. Now look, here's a ketone. Carbonyl, carbon and a carbon on the left and the right hand side. That's a ketone. Aldehydes are very similar, except for directly bonded to the carbonyl carbon is a hydrogen. That's what gives it away as an aldehyde. Okay? Ketones have carbons on both sides of the carbonyl. Carbon, carbon. Aldehyde has a carbon and a hydrogen. That gives it away. That gives it away. Now, formaldehyde is a really common aldehyde. Formaldehyde. Embalming fluid is made from formaldehyde. There's also a couple more. One's called benzaldehyde. It smells like fruit. A lot of your aldehydes smell really pretty. They have a really nice aroma. Aldehydes, ketones, what else we got? Let me think. Aldehydes, ketones, oh, esters. No, acids. Let's do acids first. carboxylic acids. Now we have a carbonyl. So there's my carbonyl again. See how it's everywhere. There's a lot of functional groups that have carbonyl, or a lot of classes of compounds, excuse me, have carbonyl. On one side is a carbon. On the other side is OH. So now you're tempted to call it an alcohol because it has this OH thing here, right? But now alcohols are like this. No carbonyl. No carbonyl, that's an alcohol. Alcohol, or the OH directly bonded to a carbonyl, that's called a carboxylic acid. Okay? They're different. Alcohols and acids are different. So here, the carbon has no carbonyl, we call that an alcohol. Here, it's bonded directly to a carbonyl, that's a carboxylic acid. The most common one that we have in our society is this one. That's acetic acid. If you buy a 5% solution of acetic acid, that's called vinegar. That's called white vinegar, actually. It's called white vinegar. 5% solution of acetic acid in water. Answer to that, I guess, in water is white vinegar. Okay, so we eat that stuff. That stuff tastes really good, actually. You know, who doesn't like a little vinegar, a little pickle action going on in your life, right? If you don't like pickles, we need to talk. Okay, so that's a carboxylic acid. Now, if you drink acetic acid, you will not get drunk. If you drink ethanol, you will. They're very different. If you drink too much vinegar, you will get sick really quick and probably have to go to the hospital. If you drink too much alcohol, well, yeah, you can get sick too, but anyway. One, you're sick and at least, you know, somewhat tipsy. One, you're just plain sick. What else we got? Acids. How about esters? Esters. What? Wow, there's a lot of names here. There's a lot of structures too. Which is why your professor, me, put on Desire to Learn some flashcards and some study aids so you can learn these things. They're on Desire to Learn. Just look at the content of the course. I think they're called flashcards. There's a bunch of flashcards that will help you learn the classes of compound. Okay? They're digital flashcards. If I were you, I would make my own little personal flashcards. At least 10 points in your exam. And ester has a carbonyl. There it is again, carbonyl. Now, it has a very similar structure to a carboxylic acid. Here we have a carbonyl, and I drew an oxygen right here. But on the oxygen is another carbon, not a hydrogen. Okay? It's not a hydrogen, it's a carbon. And I don't actually know a common ester in our society and what it's used for, so I'll just draw an example of a simple one. I probably should look up a common ester so I can be more interesting, but I don't know of one. I'm sure there are hundreds of them out there. Probably using flavoring. Okay, what else we got? We got esters. There's a lot of them. I'm just trying to think of the cool ones. Amines. Carbon bonded to N. That's an amine. Now, you could have a primary amine. Now, it's a primary amine because it only has one carbon and two hydrogens attached to the nitrogen. That's called a primary amine. A secondary amine has, this is secondary. A secondary amine has two carbons and one hydrogen on the nitrogen. It's a secondary amine. And there is a tertiary amine. primary, secondary, and tertiary amine. The tertiary amine has 3 carbons attached to the nitrogen and no hydrogens at all. Now this one I want to stop for a second and show you a couple of cool examples. Because no one believes me when I tell them this stuff, so I had to go to Wikipedia, which, by the way, Wikipedia is not a great source of information, but I don't think many people lie about chemistry, so I think we're good. Let's start here. This is a compound known as an amine. This is a type of amine. So you have an NH2 on the left and an NH2 on the right. So it's got 2 amines. That's no big deal. Same compound, 2 amines, no big deal. They're both primary, right? They both have 2 hydrogens, 1 carbon. Y'all follow me? That one is called diaminobutane. That's its chemical name. Now, let me flip back. And you tell me its common name. How's that pronounced? Putrescine. What do you think it smells like?
Bad.
Oh, where does it say it now? Is a foul-smelling organic compound that is related to cadaverine. Both are produced by the breakdown of amino acids in living or dead organisms, and both are toxic in large doses. The 2 compounds are largely responsible for the foul odor of putrefying flesh, but also contribute to the odor of such processes of bad breath and bacteria vaginosis. Yikes! Wow! Tell me amines aren't cool, man. That's wicked. Here's cadaverine. Look at that. It's also an amine. Have I convinced you that amines stink? They smell really bad. Most of them smell like urine. These ones smell like dead people. Yeah, right? This one's called cadaverine. Isn't that cool? Cadaverine. Cadaverine is a foul-smelling diamine compound produced by protein hydrolysis during putrefaction. Nice, eh? Now you tell me. Ain't that cool? That's wicked, right? Now, come on, that's actually pretty cool. Come on, you have to admit it's at least a little bit cool. You know, I'm sure everyone's smelled putrefying things before. You know, it's nasty, right? But that, it's chemistry. It's just a breakdown of your body. Which, if you ever wonder why we bury people 6 feet under the ground, that's one of the reasons why. It's stink. And no one really wants to see anyone getting eaten by a wolf or anything. Someone's poor relative being chewed up by a scavenger. Okay, so that's amines. What else we got? Oh, we got amides. Amides. Now these are interesting. Amides are interesting. Now amines are too, because they stink. And believe it or not, we have a lot of amines in our body. We have these things called amino acids. The word amino means amine. We have tons of them. Amides. Amides are like this. Carbonyl bonded to a nitrogen. Now, ester, we've already done, is that. An amine, here it can be hydrogen or carbon. And over here, another one. Now, amides, are what hold our proteins together. So we have a bunch of proteins in our body, right? They're all made up by this bond right here, the amide. And here I'll just draw you a simple amide, nothing special about it really. But this little bond right there, the amide bond, I don't think I'm exaggerating when I say it's responsible for all life. If we didn't have the amide bond, we wouldn't have proteins, we wouldn't have enzymes. If we didn't have those 2 things, we couldn't actually be alive. Now, gene jockeys will tell you that DNA is responsible for life. I say DNA is responsible for coding the things that give us life. They go hand in hand, but these are important too. And amides hold them together. Amides make them exist. Isn't that cool? That's pretty neat, right? Now, come on. Where else but Broward College can you hear about cadaverine and putrescine? I mean, nowhere, right? That's just wicked cool. If you ask me. Which, of course, none of you have, but I'm going to offer my advice anyway. All right, so that's the end of chapter 10. We are immediately going to jump into the next chapter because we don't have time not to. I wish I could go a little slower for you guys, but unfortunately we just can't. But I will hit the high points, I promise. Which means you should pay attention to the high points. Because they are important. All right, where are we? All right, oh, here, and this is your slideshow flashcards. Here they are right here. Go in here, click on that, and they should pop up. hopefully. There they go. So here's my flashcards. So a tertiary amine, you want to show it to you, just click right here. Go to the next one like that. So ester, tertamine, primary amine, ether, alkene. So what I want you to do is say, here, a primary amine. On a piece of paper, I want you to draw what the functional group or the class of compounds looks like. And when you think you've got it right, click show. And that's what it looks like. The R group, R, for those of you who don't know, R means anything. So any alkyl group, so any carbon-bearing group, basically. So when you see R, just think anything. Okay? So the next one is a secondary amine. Let's do something interesting. Carboxylic acid. So I want you to think in your mind and write down on a piece of paper and look it up if you have to, what a carboxylic acid is. And then when you're convinced that you know and have it right, show. That's a carboxylic acid. Again, the R group can be anything. CH3, CH3, CH2, CH3, a lot of stuff. Okay, so don't worry about R group so much, just worry about the main components. Okay? So far so good? So please go and do that. That will definitely help you for the exam. Definitely help you. Alright, what's next? What's the next chapter? 13? Why not, right? What?
Yes.
Sound good? I can do any other chapter if you want, but I'd rather do 13. Oh yes, carbohydrates. Doesn't that look good? Get some potatoes there and some bread, a big old bowl of pasta. Good. Now, carbohydrates. You've all heard that word before, yeah? You've all heard that people are taking these diets where they cut out all carbohydrate. I always marvel that they're still alive because they obviously haven't cut out all carbohydrate or they would be dead. Carbohydrate. Now, I will just tell you a quick story because I think it's kind of funny. I was sitting around a campfire one day when I was quite young and quite brash, brazen as well, rude probably. And these people were sitting around and they were saying how they lost all this weight by cutting out completely carbohydrates from the diet, which I just giggled at. And plus we were around a campfire, so obviously we were consuming adult beverages. I was 23 at the time, so it's okay. So I just giggled at it, just ignored it. It was a stupid thing to say. And then this person went further to say that carbohydrates were a man-made invention from the 70s by the government. I think he blamed George Bush. Like, love George Bush or hate him, he didn't invent carbohydrates. Al Gore didn't invent the internet. George Bush did not create carbohydrates. Carbohydrates have been around since the dawn of man. Before we existed, carbohydrates were here. Carbohydrates are necessary for life. They were not a man-made invention. They were made by nature. Why? Because they store energy really well. We eat carbohydrates to get energy from them. Now, what he meant to say was that refined sugars are a man-made invention. Not really. I mean, refining sugars, I wouldn't say we invented it, we discovered it. Okay? So refining a sugar, making table sugar, is more of a common technology. But it wasn't made in the 70s. It was made quite earlier than that. But anyway, so that kind of irritates me when people say stupid stuff like that. So here is what carbohydrates are. They're a major source of dietary energy. Major source. Made from the elements hydrogen, carbon, and oxygen. And look at that big word there, saccharide. They're usually called saccharide. Saccharide means sugar. Now, I don't think I'm embellishing this when I say humans, and I would say all animals, maybe there's some that aren't, but most of them, maybe some sea animals that live off something else. But I would say all terrestrial animals live off of carbohydrates. We are designed to burn carbohydrate. Our body, I don't think I'm exaggerating, is addicted to carbohydrate because that's what we use for energy. Now, is it any great surprise that every successful people group, which is all of them now, because we've all survived this long, have found a way to store carbohydrate for a long period of time? The Asian society stored rice. The Latin society, same thing, stored rice. The Northern Europeans, potatoes. The Southern Europeans, pasta. Wheat. They found a way to store carbohydrate. Why? Because that's what we lived on, and we still live on it. Just nowadays, we don't, work really hard laboring in the fields to bring home the carbohydrates. We walk to Publix and lay it on our credit cards. You know? So yeah, when you're an Italian guy back in the day farming the land, you needed a big bowl of spaghetti to keep you going. Because you needed all the energy because you're going to burn it all. Nowadays, you get a big bowl of spaghetti, eat it while watching TV, and then fall asleep. Right? And I'm not going to judge anybody. That's fun.
I do it.
That's awesome. And what do? We grate cheese on it to make it even better. Right? What else do? We throw a hamburger in there because that tastes even better. And then we drink a beer with it. Because that's another form of carbohydrate, right? Which was one of the theories why beer was invented, was to store carbohydrates, to store wheat, to basically make bread. But anyway, that's another theory. So carbohydrates are necessary. We just don't have to eat so many of them because we don't actually work that hard. So it is probably better to cut out, especially refined sugar from your diet, but you can't get away from it. Now, write these words down. Monosaccharide, disaccharide, polysaccharide. And while you're writing them down, think about it for a minute. Why is it beneficial that we run on carbohydrate? Think about that. I'm not going to answer it. Think about it tonight. Because I have my own theories, you may have your own. There's lots of reasons why. Alright, monosaccharide. A simple carbohydrate. One sugar. Simple monosaccharide means one sugar unit. I can always spell this word wrong. S-A-C-C. One sugar unit. Disaccharide. Two sugar units. So there's two sugars bonded together in some fashion. And a polysaccharide many sugar units. Many sugar units bonded together. Now, the interesting thing is that a monosaccharide cannot be broken down any further by what's called hydrolysis. And I'll explain hydrolysis here in a second. A disaccharide can be broken into two sugar units. So there's two sugar units that are bonded together. Disaccharide under hydrolysis, I'll explain this word in a minute. Under hydrolysis will give you two monosaccharides. Two monosaccharides. A polysaccharide, once you do hydrolysis, which I promise I'll explain it, many monosaccharides. Now the word hydrolysis, we're going to get into a little bit heavier than this, but right now, just look at the word hydrolysis. The prefix hydro simply means water. Lysis means to cut or to break. Okay? Hydrolysis, water breaks. Okay, so hydrolysis means you can react it with water and typically acid, and you can get breakdown of the sugar, of the saccharide. So you go from being a disaccharide, do a water breaking reaction, and you get two monosaccharides. Here you have many sugar units bonded together. Do a hydrolysis, you'll get many monosaccharides. Okay? So that's basically the first step in digestion. Is that kind of okay with everybody? Yes. Everyone kind of satisfied with that? Mm-hmm. All right, let's keep on going. Now, don't write this down just yet. I'll tell you what I want you to write down. First of all, I want to talk about these strange little pictures on the right. Let's talk about those strange little pictures on the right. Strange, strange, strange little pictures. Write this down in your notes for me. Fisher. Projection. A Fisher projection. When we look at a sugar, sugars have many carbons, many hydrogens, and many oxygens. They have a lot going on. And to look at one can sometimes get a little bit confusing. So what we do is we use what's called a Fisher projection. And I'll just draw one right quick. I'll just draw that one. I'll draw one, then I'll explain what you're looking at. OH on both sides. Okay. OH. That's a Fisher projection. That's a simple Fisher projection. Now what that means, what that literally means, is that you have that structure right there. So this and that are both technically Fisher projections, but this one is the most common way of expressing them. Fisher projections. Okay? That's one simple way to look at a sugar structure. The other way is called a Hayward structure. O-R-T-H. In a Hayward structure, they look more like this. And we're going to get into these a little more too. And for now, those are your two basic types of examining carbohydrates or sugars, the Fisher and the Hayward structure. And both have their pitfalls and both have their advantages. And we'll use them. We'll use the Fisher for some things, and we'll use the Hayward for other things. Okay? But just put them in your notes, get an idea what they look like. On an exam, I may ask you, and I may put this down here, just draw that and say, what type of drawing is that? And you'll write Fisher projection. And then I may ask you something else about it, which we'll get into in a moment. I may have this here, I say, what is this drawing called? You'll say, that's called a Hayward structure. Okay? Just so I want you to be able to identify them like that. Now, actually, I'm just going to jump over this. It's not that important. I wanted to see the high notes here, the ones that I know you're going to need to know. Aldose, ketose, Fisher projection, this is where I want to be. All right. Fisher projection. So, I've just explained them, but now we're going to talk a little bit more seriously about them. Now, I would like for everyone in this room to do a little exercise with me. I would like you to put your left hand and your right hand in front of you. Okay. Now, don't worry about hangnails or nail polish or anything like that. Just in general. Is your left hand the mirror image of your right hand? It is, right? Now, without breaking your arm, I want you to make your thumbs point in the same direction and your palms point in the same direction. Can you? You can't, can you? It's impossible. But they're mirror images, so aren't they the same? Stretch your head a little bit, right? They're mirror images, shouldn't they be the same? They're not. I can't make this one point the same direction as that one and have my thumbs line up. Confused now. What's going on here? Okay. What's that? Now your fingers are pointing in the wrong direction. See? It can't be done. Isn't that neat? Can your left foot fit in your right shoe? No, it can't, can it? It's because they're the wrong shape, yeah? Well, listen. All right, but you follow what I'm saying, right? Your left hand and your right hand are definitely mirror images, so they're similar, but they're not the same. That's important. That is called chirality. C-H-I-R. Chirality. C-H-I-R-A-L-I-T-Y. Yeah, chirality. Read that up there. Chirality. If you are chiral, you have a mirror image that won't overlap you. That won't overlap. Let's just leave it like that. Now we say it a little differently in organic. We say it with a little more, a few bigger words or whatever. We say non-superimposable mirror image, but we're not going to use those kind of crazy language here. We're just going to say it doesn't overlap. So your hands are mirror images, but they don't overlap. Little hand drawing. They don't overlap. So they're different, right? They're definitely different. Your left hand and your right hand are not the same. Now why am I talking about this? Chiral. Chiral. Chiral means your mirror image won't overlap. So your shoes are chiral. Your feet are chiral. You are chiral. Now, in chemistry, or in organic especially, and in sugars specifically, we have things called chiral carbon. Chiral carbon. Now that's interesting. That means we have carbon atoms that have mirror images that won't overlap with them. Whoa! Blew my mind right there.
Carbon atom?
Chiral carbon. We'll say, it could be an atom, but we're going to say carbon. Okay? Now, a chiral carbon will have 4 different things, atoms, okay, let's just say atoms, attached. Well, let's not say atoms, say groups. A chiral carbon will have 4 different groups bonded to them. So now, looking just at these 2 sugars up here, these 2 very simple sugars. Each one, the one on the left and the one on the right, has 1 chiral center. And on a Fisher projection, the chiral centers are always the crosses. They're always right here. So right here is a carbon, and right there is a carbon. Let's examine this carbon right quick. Hydrogen, OH, aldehyde, and this big carbon group down here. So that carbon has 4 different groups attached to it. Can you all kind of see that? The bottom one does too. CH, OH, H, and this big group up here. So there's 2 chiral carbons in that molecule. That's not uncommon. Sugars have many of them. So let's look at this one. Notice how they appear to be the same thing, but they're not. Don't they look very similar? They look almost the same, don't they? Kind of like your hands. They look similar, but they're not the same. The one on the left has the oxygen pointing to the left. You see that? See the chiral center? The OH is pointing that way. Is that true? The one on the right, the OH is pointing that way. They're different. In fact, they have different functions. In fact, they're not the same. Your body will treat them differently. The one on the left is known as L. And I'll tell you how I got there in a second. The one on the right is known as D. D and L sugars. You may have seen that on packaging or whatever. D and L. Now an L sugar is very simple. Very simple to identify them. Trust me, they're very simple to identify. What you want to do is go to the very bottom of your Fisher projection, the very last carbon, the CH2OH, the very bottom one. You with me so far? And then jump back up 1. So go to the bottom, jump up 1. Is the OH on that carbon pointing to the left or to the right? For the one on the left, the example on the left, notice the OH is pointing to the left. That's L. Left and L, L and L, L and left. See? And if you're not L, then you're D. There's no cute way to remember D. You with me on that? So let's do this example right here. On my Fisher projection, if I want to know if this is a D or an L sugar, I go to the very bottom and I jump up 1. My OH is pointing to the right, so it's D. This is a D sugar. Okay? And it's all about this chiral carbon. We're just talking about that one. Because they can be different, D or L. Are you with me?
Yes.
Now here, different sugar. Well, the same sugar actually. Let's make it different. Let's mess with it a little bit. Let's put it over here. Go down to the bottom, jump up 1. Now the OH is pointing to the left. So that's L. Make sense? That's all there is to it. Not hard, right? Everyone always says the organic chapters of this course are hard. I think they're the easiest chapters. There's no math. Yay! And right around this time is when people start wishing there was math. Alright, let's do these examples right here. Okay, let's take ribose here. Now, one quick thing. There's only one sugar I'm ever going to ask you to memorize, and that's going to be table sugar. We haven't got there yet. So don't try to memorize these structures. I don't know these structures. I'm not a sugar chemist. But I can tell you that this one right here is L or D? L. L. This one is L or D? L. And this one is? D. Not hard, right? You just identify the types of sugars you're using. L or D. Now whether it's fructose or glucose, you don't know, because I don't care if you memorize that stuff. But you're eventually going to get to the point where maybe you know that you take an anatomy, not anatomy, a metabolism course. All right, we're moving along here. Don't worry about the structure of D-fructose. Hallworth structures. Now that, as I showed you before, is a Hallworth structure. Now in a Hallworth structure, we have to start identifying other components of that, and that is whether it's alpha or beta. Now that's a weird word, alpha or beta. Let's get into that just a little bit, and then next week we'll come back to this. I'll brush on it today, I'll go over a little bit, and don't worry about any of that. And then we will come back to it again next week. So I'm just going to draw this sugar right here. Now I'm not going to ask you to ever, the slides I just jumped over, I'm not going to ask you to do it because every year I try to teach it and every year the students rebel and try to shoot me. So I decided this is not for this course. But this part you have to know how to do. So I have a sugar. And let me just draw all the accoutrement onto the sugar. And here we go down. H. OH is up here, down there. OH is here, H is there, and we'll draw it up, okay? Versus, now watch this. There it is. Now we'll draw the OH down, and everything else is the same. I'm going to give you a quick second to draw that, to draw both of them. And while you're drawing them, notice how they're basically the same, but focus your attention here and here. That's the difference right there. That should be the only difference. I haven't made any mistakes. Looks good. So just draw those in your notes, as neatly as you can.
For the test, we need to know how to draw them.
Yep, but I'm not going to ask you to go. I'm never going to ask you to go from a Fisher to a Hayworth, or a Hayworth to a Fisher, because it gets a little hairy for this level. Now in organic chemistry, we do this all the time, but even they have problems with it. It is a little bit abstract. So focus your attention on those two carbons that the red arrows are pointing to. Now, we're going to learn nomenclature for alpha and beta. Okay? Alpha and beta. Now, what do those monikers refer to? If you look at the carbon, or the Hayworth structure on the right, notice on this carbon right here, the OH is pointing up. So it's tending towards the ceiling. Over here, the OH is tending towards the floor. That's the difference, right? One oxygen's up, one is down. Do you all see that?
Yes.
So those are different. Those chiral centers are different. Those chiral carbons, the oxygen's going up in one, the oxygen's going down in the other. You with me on that? So now, if the oxygen is pointing up, so if this oxygen right here is up, it doesn't have to be straight up. Like I drew them here straight up. They could be angled up too. As long as they're tending in the upward direction, that's called beta. Beta, or that's the letter, or it's called beta. As long as this oxygen is pointing in the upward direction. Now, how do I know it's this oxygen? Or, sorry, this carbon I look at? Well, it's simple. Find the oxygen in the ring and go one carbon to the right. We're worried about that OH right there. Find the one oxygen in the ring, go one carbon to the right. We're worried about that oxygen right there. Okay? Everybody with me? Now this one is pointing down. So that's called alpha. Okay? Now, I know right now, this does not seem important. This seems weird. And why are we learning all this junk? When I see you again, and we're basically out of time, so let me just finish up. When I see you again, I'm going to talk about alpha and beta carbohydrates. Alpha carbohydrates, this one, alpha carbohydrates are usually used as food for humans. Beta carbohydrates are cellulose, structure of trees and cotton.